Alright, this is the 5.4 notes exponential and log models. So in this section you're going to be taking data sets and you're going to be using that regression feature on your calculator to come up with these models. So you might want to have it out while you're doing looking over these notes. Alright, so we got monthly premiums for $250,000 life insurance over a 10-year term period increase with the age of the men purchasing the insurance. So as you get older, the cost goes up. Alright, the monthly premiums for non-smoking males are shown in this table. Alright, so graph the data in the table as X as age and Y in dollars. Alright, so I'm going to go to my calculator and I'm going to enter in all the data. I've got it all in here already. Okay, so go to Stat, Edit, and then put all your data, your X's in Y1, your Y's in L2, sorry, X is in L1, Y is in L2, and notice that's what I've already got here. I've already got it entered in here. Okay, now we're going to put in go to our stat plot. So second Y equals is your stat plot. Alright, here's plot 1. I'm going to go in and turn it on. Alright, and then this is the scatter plot. Alright, and remember, after you've got it turned on, remember you can hit zoom 9. And 9 is, just so you know, is the zoom stat. So all you have to do is press zoom 9, and then there's our data. Okay, so obviously a line's not going to fit this, and a parabola, which, you know, a parabola goes down and it comes back up, so that doesn't fit that great either. So we can look at an exponential function that models this. Okay, so we're going to press stat. We're going to scroll right to calc. Okay, and then down here is all those regressions when we're in the calc menu. Okay, and we want to do exponential regression. All right, and press excuse me, press enter. Now, before I press enter, that is, I'm going to press vars, scroll over here to y vars, option 1 function, all right, and then tell it to store it in y1. Alright, now here is the regression it ran. Here's r squared, meaning that this is a really good model. 98.5 roughly % of the data can be explained by this. Because I pressed Y1 there, it's got it stored in Y1, so when I graph it, it'll have the scatter plot that we had before, but it'll also have that line in there as well. The exponential model. Alright, now this is basically what we're going to do for all three of these, but let me go in here and plot this. So this is age, this is the monthly premium. Notice I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of these. I don't need this down here. Alright, I've got 10 units down here. Alright, and this goes from 35 to 75, so I'm just going to go in fives. So this is 35, 40, 45, 50, and so on and so on and so on. Okay. Now, this is a huge scale. Okay, so I'm going to make this go in 500. So 500, 1,000, on and on and on. Alright, so this is part A. I just did it here. This is age in years, so I went from 35 to 80. Alright, I only needed to go to 75. This went from 500 to 4,500. Alright, and again 4,400 is the highest we went, so we almost got there. But anyway, notice it starts off almost linear and then it bends up pretty fast. And this is the characteristic of exponential graph. Right, and then part B wants us to come up with the model that models this, and that's in our calculator. So you press your Y equals, let's round it to the nearest thousandth, so 3 decimal places. So we've got Y equals, again if we pull that up there, 4.039. So 4.039 times, and in the parentheses this is 1.095. again to 3 decimal places, to the x power. Alright, and then part C, if I graph that model on there with it, alright, then I'll have this thing. So if I hit the trace button, notice right now I'm in the points, L1, L2. If I hit down, now I'm on that model, and I can use it to come up with some points. Alright, and plot some of these points and then connect them. Alright, so I'm going to do that real quick. Alright, so here's our equation for part B, and then graphing them together. This is that red line. I just used some. Here's the equation. I just pressed trace, right, and then told it some points. So like, you know, if I put 45 in, oops. So I graph, trace, press down to the function, and then press something like 45, and kind of get an idea of what I did there to get my points. Okay, so 45, 236, all right, somewhere right in there. Okay, and then something like 70. Press 70, hit enter. All right, on the model, it misses that point a little bit. 2,261. So it's 70, 2,261. So it's a little bit below what this was for 70. Okay, but that's the idea here. You just press trace, plot some points, and make the graph. All right, for the next one, find an exponential function that models the data for this data set. So once again, we're going to throw it in our calculator, run the regression for exponential regression, and then plot it. Alright, so once again, I put all my data in here. I press stat, scroll over to calc for regression, and come down until you find exponential regression. Alright, option 0 on a TI-83, but I think it's different on an 84. So vars, scroll right to yvars, function, enter, right, and then y1. Press enter. Alright, and then again zoom 9 for stat. Alright, so there's our regression model this time. Alright, notice this time it hits the data points extremely well this time. Okay, so what is our exponential function that models this data? Press your y equals, and there it is. Okay, so just write that out, and that's your answer to part 1, part A. Alright, so there's our answer to part 1. Alright, part 2, just come down here, number your axes. 1, 2, 3, 4, 5, 6, 7, 8. Alright, and then this is getting smaller, but again, we don't need to go any higher than 780. So this will be 100, 200, so on and so on and so on. Alright, now we're just matching up points. So 1, 781, there's 800. So 780 would be somewhere around there. 2, 608, there's 600. 608 is just barely above it. 3, 475. Alright, 4, 370. 5 is 289. Alright, 6, 225. 7 is 176. 8 is 137. Alright, so there's our points, and then we're graphing the data and the model on the same axis, so we want to graph this on there with it. Alright, so again, use your calculator. You got the graph of it. Press the trace button. Make sure you press down, because if you don't press anything, it's going to not understand what you mean. So press down so you're in this model, and then press some numbers. So 1, 779 instead of 780. Alright, almost virtually the same point. 2, 608, 608. I mean, this is going to be really, really close. 3, 474, 475. I mean, it's virtually the same thing. Okay, all the way down through here. 370. 5, 288.7, 289, 6, 225.28 versus 225, 7, 175.7, 176, and then 8. 137.09, 137. So I mean, it's basically is the model. So I'm just going to use a red line here and just basically use the points that I'm already given. Alright, then putting them on there together looks a little something like this. Alright, now exponential models, basically what we've been doing, have this look to them. Something times 1 plus or minus some rate of change to the x power. Okay, so this is what growth looks like, something bigger than 1. We added something to 1. This is what decay looks like. We subtracted something from 1. So if you look at those last two models, this was exponential growth, 1 plus some change. Right? This was exponential decay, 1 minus some change. Here we're subtracting like 22% roughly. So this was like 22% decay rate. This was like a 9.5% roughly growth rate. So that's what we're talking about here. So whatever R is, like for instance in the first example, say R equals 10% growth. Then we would use the top model, alright, and we would say Y equals A times 1 plus 0.1, alright, 10% as a decimal is 0.1 to the x, which means A times 1.1 to the x. Alright, and if it were decay, if I was going to do a decaying function, so let's do like R equals 23% decay. Then we would use Y equals, now we're using the bottom one, Y equals A times 1 minus 0.23 to the x, which would be A times 0.77 to the x. Okay, so that's what these models look. We're not going to write them 1 plus 1 minus unless it's something like compound interest. We actually do write it 1 plus, but in this case usually we do the subtraction if it's just a simple decimal that we add or subtract from 1. Alright, so for an example, suppose inflation averages 4% per year from 2000 to 2010. This means an item that costs $1 will cost $1.04 a year later. Alright, $1.04 squared 2 years later. So write an exponential function that models the cost of an item t years from 2000 if its cost was $100 in 2000. So for A, alright, we started off with, if we look at our definition of the model, it's growing by 4% per year, so we're going to use that top model. Alright, and we're going to say that cost, we'll use C, equals, we started off with $100 and we grew by 4%, so 1 plus 0.04, which is 1.04 to the t power. Alright, and then use the model to find the cost of the item from part A in 2010. Alright, what does t represent? Is years from 2000, so we're going to put a 10 right there. So C is equal to $100 times 1.04 to the 10th power. Alright, go to your calculator and put in exactly what you see there. So back to the main screen, clear, $100 parentheses 1.04 raised to the 10th power. Alright, that gives us 148.02 roughly. So $148 and a couple pennies is our cost in 2010. Alright, nothing to this stuff, not too bad at all. Alright, this table projects, gives projections to indicate the percent of U.S. adults with diabetes could dramatically increase. Alright, and we want to find a log model that fits the data with x equals 0 being 2000. Okay, so what I've done first of all here is on this second page I've changed it, because here it says x is 2000. So instead of writing in 2010, if x is 2000, then 2010 would be 10. Okay, 2015 is 15, but the same exact data set as far as the percents go: 15.7, 18.9, 21.1. Okay, I've just changed the x's to what we're going to use to model it. So this is the stuff that's actually going to go into my calculator. Alright, so I've got it all in here, and I'm going to, part A is wanting us to find a logarithmic model that fits the data. So for a log model, again, you press Stat, you come over to Calc, and we're going to scroll down until we see LN regression. Okay, now there's logistic, that's not it. Okay, make sure you use LN regression instead of logistic regression. That's two different types of models. So LN REG. Alright, and again, I'm going to press vars, yvars, function y1, and that way it'll plot it for us. Alright, so there it is. There's our model, R squared 0.98, very good fitting model. If we graphed it, zoom 9. Alright, there's our data set. There comes our log model. So it hits most of the points fairly closely, kind of misses a couple here and there, but still, that's a really good fit. It's a good model, could predict the values pretty well. Alright, so part A wants us to find the log model that fits the data. So again, just round these values that are in your y equals screen to 3 decimal places, or however many you're asked to. Alright, and again, here's all my values, so I round it to the 3rd decimal place. That gives me a 5 here. 11.851, rounding it to the 3rd decimal place, times the natural log of x. So there's my first model. Alright, then use the reported model to predict the percent of U.S. adults with diabetes in 2027, alright, which we skipped over. So again, if you've got it in there, you just press graph, hit trace. This is not the model, this is the point, so press down to get to your model. Alright, and then just type in 27. So 2027 would be 27 in here. Hit enter. So about 26.09 to 2 decimal places percent. So 26.09%, or about 26% would be good, would be sufficient here. Alright, one last thing. What year does this model predict percent to be 26.9? This is where you can use your calculator. Type in, there's your regression function. Go down to the next one. Type in 26.9. Alright, graph that along with it. Alright, and then find that intersection. So second calc intersect, option 5. Alright, first curve, that's what we want. Second curve is the 26.9, and the guess, it looks like it happens about right there. Alright, but 28.92. So remember, what year would be 28.92 years after 2000? So about 2029. Alright, rounding it to the nearest year. Alright, and then make sure you understand this. When using technology to fit a log model, you must align the data so all input values are positive. Okay? So what that means is, if I'm putting in the XY data sets into my calculator, notice I have a -1 and a 0 here. If I try to do LN regression here, log regression, it's going to tell me, whoa, you can't do this. Okay, and you go to, and well, the problem is you've got negatives here. Okay, now notice if I change this to like +3, for instance, but I still have a 0 there. Once again, if I try to run the LN regression, it's going to tell me, just like before, I don't like this. Right? So go to your, go to your editor this time, and again, now the problem is 0. If I fix that and now ran it, it can handle it. Okay, and it doesn't matter if you have negatives in your y's, like let's say this is -6. If I run it here, it's fine. It's just when the x's are negative. Okay, so make sure you understand that we can't have negatives in the x or the L1 column when we're doing this.